Hey, good morning, everybody. Hope the tests are now under our belt, and I'm sure you will find that you did quite well if you've done the homework. And there you go. Hey, our next sections are 2A, B, and C. So this is kind of that, hey, did you pick it up all last year? We hope so. And if you didn't, it's there for you. We're just going to kind of roll through it. Sets. Just got to be careful. Relations and functions. You probably run into a set before. You probably deal with functions, and believe it or not, relations are a very, very simple way of saying a set of ordered pairs. Remarkably, when you're a senior, we go back and we stop talking about functions so much, and we reevaluate how important the idea of relations are. And that's where you can open up new types of mathematics like abstract algebra, and there you can kind of look at things like the rotations of molecules and the rotation of the Rubik's Cube, and all of a sudden art and complex numbers and music have really a lot more in common than you think. So I'm going to go through this. It kind of can be a little bit dry, but understand it is the building blocks of so much cooler stuff than just squiggly brackets, which are kind of fun in themselves. All right. So a set is a well-defined collection of objects. The objects in a set are called the elements. So we will talk about elements a lot. Hey, we usually use a capital letter for a set. And in this case, I just said G. We asked somebody in class, your 3 favorite things, and they said bed, penguin, hanging chair. Those are elements. It doesn't have to be, 5, 7, 12, -3. Those are cool things too. But the more you think abstractly or as an object, the more maybe you can do with that set. Cardinality is something that's not going to be addressed, but I know it comes up later. Cardinality is just a fancy way of saying how many elements are in that set. In this case, the cardinality is 3. We kind of notice that these notation here is like absolute value. Absolute value, those symbols will come in the context of the problem and mean kind of different things, but the more you kind of generalize and put them together, some really cool characteristics. Can you have an infinite cardinality? Yes. And can you have different sizes of infinities? The answer is yes, and that is amazing. And it's just, if you want to talk about it, we can, because it is so fun. We have uncountably infinite and countably infinite. We'll move on. Hey, if X is an element of set A, that's fantastic. We write this notation. So practice it. Have your notation out and just kind of practice this little, I do a little C and then I go like that. All right. The symbol E means is an element of, and X is not a member. We put a little slash through it. So for here, we would say bed is an element of G, and we say a bike is not an element of G. Too bad. That would have made it a really cool set. Keep it simple. So number sets, these are going to be, if I use this notation, you have to understand what set of elements I'm dealing with. And this is something that we assume everybody knows, and it's no. Everybody needs to write these down, print this off, have this, and actually practice writing these. The way I make like the N, I go, so I kind of do 2 strokes. I go, I do that, and then I start here, and I go like that. That to me is way too cool. The Z, bam. The R, that's how I do my, I don't really double up on the leg, but I make sure I double up right here. Please notice that they're, everything that is something that you're used to. 0, 1, 2, 3, 4, that's great. Up, plus and minus for the integers. This is a fun set. Those of you in discrete mathematics that want to talk about prime numbers and just fantastic stuff. We'll deal with the set of integers a lot. Rational numbers are cool. And now we're using this thing called set builder notation. We're going to talk about that in a later slide. This is a set of objects. Well, every object can be taken as x. Great, we're used to that. This is, I'll go into it a little bit further, but every element of this set has this form. Every element has that form as long as that's true. Well, if you don't know what this notation means, you're kind of stuck. So you better know element of this particular set. Well, what is that set? It's this. Oh, okay. So, man, I thought you couldn't divide by 0. Oh, we do throw in the idea that the bottom number here can be anything but 0. So, is the number 5 in this set? You bet. 5 over 1 is P over Q, and we're good. Ooh, the set of real numbers. This is the number line. There are a lot of elements in that set. In fact, that is uncountably infinite. Set of integers is countably infinite. Woo! Complex. Horrible name. Horrible name. That's like naming your kid Loser. It's like, no, they're not bad. They're not like a loser. That's just a family name. Loser, It's too bad. Complex, that's hard, difficult. No, it should be the set of beautiful numbers. Because they just have so much mysterious qualities that are so fun to go out and explore. Hey, if you write a set with a plus, you're indicating that I want all the elements out of that set that are positive. 0 is not considered a positive number. It's not considered a negative number either. 0 is considered an even number, but it's not considered positive. All right. Hey, some people like to see what sets are in other sets. And remember, this all are part of the complex numbers. Okay, so if you're an integer, you're also a rational, a real, and a complex. All right, there are a few numbers that are all of them. The number 159 is one of my favorites. That is a natural number, a whole number, an integer, a rational, and a real, and a complex. Mr. Sayers doesn't have an I. 159 plus 0i. Beautiful. Hey, a relation is a set of ordered pairs. So one of my favorite sets, a relation, is 1, 3, 4, 5. That is a set of ordered pairs. So all it is, there's no rule or anything. You can just have a list of ordered pairs in there. Now we may want to make a rule that creates all their ordered pairs, but we're not doing that. We can do this if we want. A special function, a special relation. So I'm trying to give you kind of an order of generality. A function is nothing more than a special relation. Well, what's a relation? A set of ordered pairs. So now we're dealing with ordered pairs. A function is a special one where no two different ordered pairs have the same x coordinate. In other words, you can't map the number 1 to 5, and you can't have, so in a relation, if you have 1, 5 and 1, 6, ... that would not be a function. It's definitely a relation, but since 1 is mapped to 5 and 1 is mapped to 6, that's 2 time and no good. Every function is a relation, but not every relation is a function. So you're kind of la-la land, sitting there going, no, where am I going to be? What am I going to have to do? Just kind of relax and let it kind of come in here. First thing you're going to be asked is, you're going to be given a relation, set of ordered pairs, maybe in a graph form, maybe as an equation form, maybe just a set of ordered pairs. And what you need to do is be able to say, hey, that relation or set of ordered pairs is a function. All right, the first one is algebraic. Certainly get paid a ton more money if you can do this. You would just have to ask yourself the question, if I plug in an x value, will I only get one y value back? If I plug in an x value, will I only get one y value mapped to it or with it? So for this one, if I plug in the number 2 and multiply it 6 minus 1, I get 5. That is the only thing I'm ever going to get if I plug in 2. And in fact, I can generalize and say, hey, if I plug in any value, I'm only going to get one value for the y. Now, if I plug in something here, will I only get one value for the y? Well, let's say I plug in the number 4. What's my value for y? Well, when I solve this for y, I do plus or minus the square root. So I'm going to get actually 2 values. So in this relation, you would see 4, 2, and you would see 4, negative 2 if you listed out all the possible ordered pairs. Boo. I mean, not boo like bad, you're a bad function or a bad relation. It's more like, oh, darn it, that relation doesn't make the club of functions. We love the vertical line test. If we're given a graph, that is, man, I'll bet most people are kind of nodding their head and going, yeah, I've done this. All you got to do is draw a vertical line. If anywhere on the graph, only even just once, do you cross that graph twice, that means for that x value, you are assigning 2 different y values. It's not a function. We love that one. All right, graphical note, if you see a graph that's and then has this open dot, that x value right there is not part of what you're plugging in, so it's off limits. Okay, if it's filled in, then definitely that's part of it. You wouldn't see it filled in when it connected, but maybe you go like this, then you have this open dot and it continues. For that x value, it's only on that graph once it's here. But man, if it was like that, then it would not be a function because it would not pass the vertical line test because it would hit here and here. All right. So function notation, what are we used to? I'd say most people are used to this. Most people are used to this. This kind of notation is, definitely a higher pay grade than this. But it means the same thing. It's a function. The variable in the function is x. Whatever we want, we plug it in, we get something, and the result is our function value, or what we call the y value a lot of times. This is definitely new, and it means the same thing. So don't go, oh, okay, this is something totally different. No, it's just notation. Now you want to get paid a little bit more. You got to step it up with a little bit weird, challenging notation. It's still got a name, f, so that and that are the same. It's still saying, hey, we're going to have the values of x, and what those values are going to be mapped to or paired with comes from this expression. So if I plug in 1, I plug in 1 here and I get 5. That means that the ordered pair 1, 5 is an element of that relation, and it just so happens this one's a function. All right. I would say most people feel pretty good about if I say f of 2, that means plug 2 in, and we get 5 minus 2 minus 2 squared, and we get a number. Awesome. Way to go, Mr. Sayers. You're A for the day. Some people start to kind of get a little bit nervous. I'm going to have to edit that out. I messed up, didn't I? Maybe I won't edit it out. Where did I mess up? Right there. Now let's go back. All right. If you want to do f of negative x, then you would plug in 5 minus negative x minus negative x squared. Hey, use parentheses. That's going to kind of keep you honest. 5 minus a minus is a positive, minus negative x times negative x is positive x squared, and you're done. That's it. F of x plus 2 would be, whatever that is, plug it into this formula, 5 minus, and then I see a variable there, so I plug in whatever I want, x plus 2 in this case, minus x plus 2 squared. Hey, I'd love to call that the answer, but we're going to want you to multiply that out. All right, finally, the last section, domain and range. I'm going to pull your eyes to this. The domain is a set, so what we're going to be talking about is a collection of objects. Those objects are probably the numbers that we can plug into the function. Okay, I'm already saying it's a function. I could back up and say relation. The range is really, if I'm plugging the x values in and mapping it to the range of the resulting values. But more generally, it's just the y values, or the second value in the ordered pairs. All right, notation. Don't let it get in the way. When we talk about sets, when we've got to be very careful about how we write it. So if we tell the world these are the numbers, all numbers including a to b, this is a very famous way to do it. We're implying all real numbers, and that's really cool. All right, this, ladies and gentlemen, is called interval notation. Interval notation. All right, so what are we gonna, what are the meat and bones about this? Is it's a set. We're saying, hey, all the values are going to be elements of this interval. So how do these brackets work? Well, A and B are pretty obvious. They're going to be the endpoints of the interval. That's great. But now we have a very select bracket. And the bracket can be either in towards the two numbers, or it can be facing out. And all that means is if it's facing towards the two numbers, that means it is inclusive. Or if it's facing out, that is exclusive. Exclusive. So a quick example, here's the number 2, here's the number 3. Let's say this is an open dot and this is a closed dot. And I want to tell the world that the set is from 2 to 3, and it takes 2, but it doesn't take 3. So I could do what we usually do, greater than 2, less than or equal to 3. So that means x is between 2 and 3, but it doesn't include 2 because that's just greater than, but it could include 3 because we have the equals. All right, so the interval notation is x is an element of, so it's part of this interval. I like to write the two numbers that are involved, 2 and 3, and then I decide, are we including the endpoints or not? Well, if we include the endpoints, we make the brackets face the interval. So that would be the 3. But we want to tell the world that it's really close to 2, but it doesn't include 2. So we make the bracket face out of the interval. So that and that are the same thing. That and that. Now, if you're looking here, we want to tell the world, hey, x can be less than a or it can be greater than b. X is less than a or greater than b. So x is an element of whatever this says. Please understand this is one interval and this is another interval. That u right here just means or. It can be in this interval or this interval. The way it looks with the brackets, it's like the brackets are around that u, and that u is really important. That u is separate from the two intervals. All right, so it says it's going all the way to negative infinity, all the way up to our a. That's great. And then it starts at b and goes to positive infinity, and that's really what we see. Does it include A or B? No. That right there is facing out from the interval. That means it doesn't include A. And this is facing out from the interval, so it doesn't include B. Mr. Sayers, does it include infinity? Basic rule is no, we never include infinity. Let's do a few more examples. All right, you're going to be asked for the domain and range of graphs. So I have the answers under the blue box, but I'm gonna walk you through and write a few. All right, so the domain are all the x values. So I see the x value here is -1, and this arrow right here means it's going to go on forever. So every x value from here over is going to be on there. So, and it's included. So we could do a number line and just say -1. That's one way to say the domain, just kind of graphically, but we're going to step it up. We could say, hey, x is greater than or equal to -1. I think that is the most common. It's the most straightforward. I love it. Next is set builder notation. We haven't talked about that, so please pay attention. We want to talk about a set. All right. When we talk about a set, we got to do our curly bracket. So that is going to say, hey, all the elements of the set are in here. Practice that. You're going to say x. So that's just a formality saying all the elements can be x. And then a straight line or a colon there will say such that what follows is kind of the characteristics. X is less than or equal to -1. You're like, seriously, you got to be rolling your eyes a little bit. Why don't we just do this and not worry about the set builder? Because when you're walking through the woods and you see this, you better know what's going on. And all your friends who are not paying attention be all nervous and lost, and you'll be like, settle down, I got you. All right. And finally, interval notation would say x is an element of, now this is the world, you got to tell the world from -1 to positive infinity. So go ahead and write the -1, positive infinity, and then ask yourself, are we including the -1 or not? And we are including it, so the square bracket faces in. And we never include infinity because we never can be the biggest number. So we just, by formality, say up to, but not including infinity because we can never get there. I know you're doing great. I know it's weird, but it's fun too. Let's look at the range. We better change colors. All right. The range are all the possible y values. And if you're looking at the y values, you notice that the lowest it can be is -3. And if this continues up, it certainly goes from -3 up. So I'm going to do this pretty quick. I'm going to say y is greater than or equal to -3. The set builder notation is all the elements y such that, well, what's cool about these values y? Well, they're all greater than or equal to -3. Wow, that's cool. And then interval notation would be y is an element of. The lowest value is -3, biggest value is infinity. Do we include -3? Yes, we do. Too bad, we never include. All right, let's try another one. All right, we're talking domain and range, domain and range. So ask yourself, what x values can be on that graph? Remember, this arrow right here means it continues. It doesn't just vertically drop off, it moves. So basically every x value is on that graph somewhere. So how do we tell all x? You can write in English all x values, but we want to step it up a little bit. If it can be any number, we'll just say that it is any number of the set of real numbers. That's basically saying anything on the number line. That's pretty cool. There's really not I mean, you could, yeah, you could do set notation or set builder notation and do something like that. That's fine. That's fine. You won't see this, but you're like, oh, how do you do it? Interval notation would be x is an element of negative infinity to positive infinity. That's just messing with people. I love it. That's your MO. All right, the range. Once again, you're asking yourself, what are the y values? The y values to me are the highest it goes is 1, and every y value below that is hit. So I would say y is less than or equal to 1. Mr. Sayers, is that an open dot or a closed dot? It's got a little blue in there. I thought it was open dot, but after doing all the problems on the homework, I found out that they mean that to be a closed dot. So if it's obvious that it's white inside, then it's open, but they're going to consider that a closed dot. So set builder is, whoops, forgot my bracket. Y is less than or equal to 1. And finally, y is an element of from 1, so we don't say 1 to negative infinity. We want to go in kind of order. So that would be negative infinity to 1. We never include infinity. Do we include the 1? Yes, so the brackets go toward the interval. You might be done. You might be like, wow, Mr. Sayers, you're kind of pushing the time, but you might need this. So I'll do one more. This is a pretty cool one. Domain. What values of x are on this graph? Everything but 2. That's called an asymptote. Just saying, hey, you can get really close, but don't touch. All right, so x, so a very, very simple one here is x is not equal to 2. Yes, could you say x is less than 2 or x is greater than 2? Absolutely. Could you say x such that x is not equal to 2? That's the best. And all right, I know. What do you do, interval? Let's try it. X is an element of the interval from negative infinity to positive 2. Do we include infinity? Never. Do we include 2? Not in this case. But that is only the left-hand side. We're going to do union, which means or another interval. That interval is 2 to infinity. Do we include the 2? No, so we make the brackets out. Do we include infinity? Never. The formal. There you go. So I spread this out to really show that we have this interval and this interval, and this is an or, meaning it can be in either one of those. I think at this stage maybe you could pull off the y value. There is your assignment. I think you got it. I think there will be questions. Good luck with the notation. That's critical. Thank you. See ya.